Welcome to the Space Telescope Public Lecture Series. Tonight, A Drop in the Light Bucket. How do we measure a galaxy? By Amanda Pagul of the Space Telescope Science Institute. I'm your host, Dr. Frank Summers of the Office of Public Outreach. It is my pleasure to bring you the Public Lecture Series each and every month, along with our amazing tech team, Thomas Marufu and Grant Justice, who enable this webcasting to go out both through the Space Telescope webcasting site and through YouTube. I will remind you that the Space Telescope Public Lecture Series will continue to be online only throughout 2023. Our upcoming talks. Next month we have a special presentation for you. This will be a special event during the Roman Science Conference that will be held here at the Space Telescope Science Institute. Therefore, it is not on the first Tuesday as usual. It is actually on the third Thursday, or maybe that's the fourth Thursday, June 22nd at 4:30 p.m. That is to correspond with their conference. And you get two, not just one, you get two talks for the price of one on this. They will have Joan Gordon speaking on the personal side of Nancy Grace Roman. So that is the history behind the woman who the Space Telescope is named for. And we have a speaker yet to be determined who will talk about the mission and the science that will be done with the Nancy Grace Roman Space Telescope. So it's going to be, at least 6 weeks, maybe 7 weeks between this public lecture and the next public lecture, but that's because we have a special event for you in June. In July, you have this guy named Frank Summers, which would be me, talking on a visualization that we have done and the detailed science behind it and all of the multi-wavelength exploration that we've done with it. Stefan's Quintet, a multi-wavelength exploration. In August, we have another special event, as it will be just over 1 year since the Webb Space Telescope started taking science observations. So on August 1st, we have a talk entitled Webb Space Telescope, the First Year of Science. And unfortunately, that speaker is also to be announced. So look for that. I know you're not going to want to miss that one. If you want to follow along and find out about the lectures, you can go to www.stsci.edu/public-lectures. That will take you to this web page. And you can see that our webcasts are in the lower left. And if you'd like to sign up for our email announcements, you can sign up in the lower right. Also on that page are the list of the upcoming lectures. And if you click on any one of those lectures, it will give you the details, including all of the description about it, as well as after it has been recorded, links to the Space Telescope webcast, as well as the webcast out on YouTube. Our email, as I said, the announcements, you can sign up on the website. You can also just subscribe to our YouTube channel, youtube.com/Hubble Space Telescope. If you sign up for that, you will get notices of our new videos and reminders of live events such as this. Also, if you have comments or questions, you can send them to our email, which is publiclecture, all one word, @stsci.edu. If you would like to follow our institute on social media, we do social media channels for the Hubble Space Telescope, for the Webb Space Telescope, and for the Institute, the Space Telescope Science Institute. And we are on Facebook, Twitter, YouTube, and Instagram. I myself don't really do much social media, but I have the accounts just in case. I'm do a little bit on Facebook and on Twitter as Dr. Frank Summers. The news for the universe for May 2023. Our first story tonight. 33 years of Hubble. Yeah, Hubble was launched in 1990 and just passed its 33rd anniversary. And as you can see in this image, Hubble has produced a tremendous number of images and so many really cool images. But we still try to come up with a really cool image for Hubble's launch anniversary every year. And it kind of gets harder and harder every year, and you have to scratch your head and work real hard to come up with ideas. Well, it turns out 3 years ago, on Hubble's 30th anniversary in 2020, somebody had the cute idea to say, hey, let's go see what NGC 2020 looks like. Since it's 2020, go look at NGC 2020. And actually, NGC 2020 is right next to NGC 2014. And together, they made a tremendous image. This was what we called cosmic reef. So this sort of little bit of numerology kind of worked out for that. Well, there's a little bit of numerology used here for the 33rd anniversary. So Hubble's 33rd anniversary 2023, what are we going to do? Well, let's try that NGC 2023. Yeah, Hubble has already done it before, and there's a major problem with it. You see this big spike, this diffraction spike stretching across the image? If you actually want to look at NGC 2023, there's a huge honking bright star there. And it's not really good for an anniversary image. It's, you can't quite get it. So it's a nice nebula. Nothing wrong with this nebula. It's just got a really bright star in the field. That doesn't quite work with it. So then you say to yourself, well, maybe 33, right? There's this Messier catalog. What's Messier 33? Unfortunately, we've already done Messier 33. Messier 33 is the Triangulum galaxy, and Hubble has done this in spades with hundreds and hundreds of millions of pixels. So yeah, we can't use that again. We've already used that for it. So you'll work hard and you'll think and you try and you're going to, and then you get to something called NGC 1333. All right. And Hubble had looked at that nebula before. And here are 2 images from it. And they're not terribly exciting because they're sort of in the outskirts of the nebula. But when you look at the real nebula, you got something. So for this year's anniversary image, Hubble created this image of the nebula NGC 1333. Ooh. Yeah, this is cool. All right. So NGC 1333 is technically just this blue region up at the top. It's what's called a reflection nebula. There's that bright star, and the light of that bright star reflects off the gas around it, okay? And that gas shows up as blue, all right? So you've got a reflection nebula at the top. But in the middle, you have dark nebula. This is an absorption nebula. This is dark, dense gas that's absorbing the light. And so you have the bright spot behind it, and the light, it's actually absorbing it. So you see the dark nebula. And then down bottom, you have the bright nebula, the emission nebula. This is a region that's inside this dark gas where stars are forming. And these newborn stars are shooting off jets and such. And so there's a lot of activity going on there. And so what that sort of makes this really cool is that you've got a reflection nebula, an absorption nebula, and an emission nebula all in the same image. And it gives you this really cool kind of effect. And I sort of think like that's sort of that looks like the moon over the atmosphere, and then there's a fire in the forest down below or something like that in a night thing. It's just really this cool contrast of the blue up top to the dark in the middle to the red down bottom. All right. And so NGC 1333 makes for a nice image on this scale. But I gotta say, while researching NGC 1333, I found this image from the Hubble Space Telescope. And you see that little orange box that I drew in there? That's the scale of the Hubble image. And what you see below it, all that green stuff, those are those newborn stars that are shooting off these jets. There are these things called Herbig-Haro objects, and there's like 9 or 10 of them in there. And so I gotta say, well, the Hubble image is really cool, and it makes for a great 33rd anniversary image. I hope that sometime for Webb's anniversary, that Webb will look at all this stuff down here, and we get a really high detailed view of all those newborn stars and all those jets coming out of it. So maybe sometime in the future I can bring that to you. Our second story tonight, expanding our view of a supernova remnant. And the supernova remnant in question here is one of the most famous. It is called Cassiopeia A. And here is the Hubble image of it from gosh, like 20 years ago, okay? And this is this circular bubble, right? Because a supernova is when a star explodes. And so what you're seeing here literally is the guts of the star blown out into interstellar space. This is about 10 light years across. So it's been expanding for about 300 years. The supernova exploded about 300 years ago, and here is the result that we see today. And Hubble's image is cool. Don't get me wrong. I really enjoy Hubble's image. It's got all sorts of fine details. But supernova remnants are generally even more exciting when you look at them in the X-rays. And so here is the X-ray image from Chandra, the Chandra X-ray Observatory. And because the gas in supernova is heated up to hundreds of thousands and millions of degrees, it glows in X-rays. So you can see all these elements that were created in the supernova blown out across space, and the different colors here actually represent different elements observed in the supernova remnant. And so the X-rays are really cool here. But what's also crazy about supernovae is that X-rays are high energy, but supernovae actually also look pretty good in low energy radio waves. So this is radio light as observed by the Very Large Array. And again, you get that beautiful bubble structure from the radio emission from Cassiopeia A. The one place where we didn't have fantastic resolution to look at the Cassiopeia A was in infrared light. This is the observations from the Spitzer Space Telescope. And, you know, you can't blame Spitzer. Spitzer has only an 80 centimeter mirror, okay? It's less than a meter. Hubble has a 2.5 meter mirror. But the James Webb Space Telescope has a 6.5 meter mirror. So that's where I'm headed on here. We now have a infrared view from the Webb Space Telescope of Cassiopeia A. And even though I've been talking a long time, it's worth waiting for. Yeah. This is the mid-infrared view with a MIRI instrument from Webb. And you can see that finely grained structure that you see in the Hubble image, but you also see all this other material that Hubble doesn't see. All right, so if I go to the Hubble image, right, you can see I called this the guts of the star that are being blown out into space. Well, those same guts of the star do appear in infrared, but then you see all this orange and reddish gas out here along the top and the left side, okay? What is that? That's the dust that has been expelled by the supernova that's crashing into other material out there and heating up. Okay, so that's warm dust material. Okay, so that's the first wave of stuff. And then you got stuff from the star. The other thing that you'll notice is if I go back to that Hubble image, oops, I have to go forward to that Hubble image, right? All right, and Webb, Hubble, Webb. Do you notice that the material looks like it's getting larger? Yes, it is getting larger. This is not just the thing. There are plenty of stars in this image, so I registered them correctly. The supernova remnant has actually expanded over the 20 years between those two observations. Yeah, this is only 300 years old. It's still expanding. So 20 years is a significant fraction of 300 years. And so you're able to actually see the expansion of the supernova remnant between these two epochs. Right. The other really cool thing in this Webb image that I want to point out is this sort of green bubble-like curvy structure here, okay? And we don't know what it is. We haven't seen anything like this before. It's really cool. The press release said that the complexity of this structure is unexpected and poses difficulty for interpretation, which is a very polite way of saying the astronomers, even the experts in this object, look at this and go, what's that? We're going to need to study that to figure out what's going on there. So not only has the Webb Space Telescope shown us the expansion of the supernova remnant, but it has also expanded the possibilities of what we can see in the infrared in the Cassiopeia A. All right, now to our featured speaker. Our featured speaker tonight is Amanda Pagul of the Space Telescope Science Institute. She is a SDSCI fellow and has only been here for 6 months, okay, which was really great because she got here and said, "Hey, Frank, I want to give a talk." And I was like, fantastic. I love it when new people volunteer to give talks. She is working. Well, she'll tell you about what she's working on. Her history is that she didn't, like me, she didn't grow up wanting to be an astronomer. I had no idea I'd become an astronomer. She left it till kind of late. She was doing pre-med at the University of Chicago, and then she switched to astronomy for her graduate work at University of California, Riverside. And she has come here to help to work with us. In her spare time, she actually does what I do, but she doesn't get paid for it. She does outreach, and she works with students and a small telescope to do outreach projects and teach students how to observe the universe, as well as, she says, to really relax, she does some knitting and crocheting. So Amanda, if you'll start your screen share. Ladies and gentlemen, Dr. Amanda Pagul. I guess there we go.
Okay, can you hear me all right?
Yes, we can.
Okay, so slideshow. Can you see my screen?
Yes, we can.
Okay, thanks, Frank. Sorry, I just wanted to double check to make sure that everyone is getting what I want them to see. Okay, so thanks so much, Frank, for that introduction. Like Frank said, my name is Amanda. I'm currently a postdoc at the Space Telescope Institute, started fairly recently. And my research work mostly focuses on understanding galaxy formation and evolution. I also help support one of the detectors on the Hubble Space Telescope called the Wide Field Camera 3 with C3. So I'm with that, I'm really excited to tell you a little bit about my research of how we measure a galaxy. And so what I want you to get away from this is we've all seen these really beautiful images that are coming out of Hubble and now James Webb. And so what I want to talk about is how do we go from those images and extract meaningful information from them. So that includes things like how far away the galaxy is from us, what is its stellar mass, how many stars does it have, how many stars does it form, so things like that, how old it is, etc. And so I guess I'll just dive right in. Okay, so before I sort of start with all of the technical information, I wanted to show you the first picture I have ever seen through a telescope. It's this picture of Saturn on the left. And like Frank said, I was never really interested in astronomy and astrophysics. It was, and I say that because it was never really an option to me. I'm originally from New York City, and I make the joke that in New York City, the closest thing that you ever see to a star is a helicopter. So it was totally not on my radar. And when I was in college, I was able to go to a place called the Yerkes Observatory, which is home to the largest refracting telescope in the world. You can see it on the right here. So if you're looking through the eyepiece, that's sort of what the bottom of the telescope looks like. It's really very impressive. And if you're ever in the Williams Bay, Wisconsin area, I definitely encourage you to stop by the observatory and check it out because it really is quite magical. And so I looked through the telescope and I saw this image of Saturn, and it was just the most sort of impressive feeling that I got. I was so blown away. I couldn't believe that this planet that's so far away from us, right? Maybe by cosmological distances you wouldn't call it far away, but in absolute terms, it really is very far away. It's around 940 million miles away from us. And so I was so impressed by the fact that we can actually see it, and that the photons or the light particles that are being reflected off of Saturn from the sun is actually coming to us, traveling those 940 million miles through the telescope, through that eyepiece, to hit your retina. And also my phone camera. I kind of like put my phone up to the eyepiece to try to get a picture of it, and that's what you see on the left. So it really was a special moment, and it totally kind of kickstarted my career in astronomy and astrophysics, and I decided to no longer be pre-med after that. Here's another picture of it. I mean, just being in that, the dome was an experience in and of itself, and then looking through a telescope for the first time it was so incredible. And I have to say, not bad for a first telescope, right? So this sort of got me thinking about, what does it mean for us to measure light? How does light travel? What is a photon, right? So when I say photon, I'm referring to basically a particle of light. I want to show you this video. This is a visualization of what the very early universe looked like. So this is around 300,000 years after the Big Bang. And in the blue, you see these, the photons. So the blue is the photons. And in the red and the green, you see protons and electrons. And the photons, I'll start the video, are bouncing all around the electrons, are bouncing all around between the electrons. And, and the reason for this is that the universe at that time was so hot and dense that atoms weren't able to form. So you basically had charged particles, or ionized plasma, basically, and that's just a fancy way to say you had a bunch of protons and electrons swimming around, and it caused the universe to be opaque. You can see why, because light had trouble trying to escape. It kept bouncing back and forth on the electrons. Eventually, it cooled down. The universe cooled down enough such that those protons and electrons got together and created a neutral universe. And finally, the photon was able to free stream out. And that is sort of the first light that we can detect with our telescopes, called the cosmic microwave background. And this happened, so that was 300,000 years after the Big Bang, right? And we're at what? Around 14 billion years after the Big Bang. So this photon traveled pretty much uninterrupted. I'm sorry, I'm trying to pause it and it's not. This photon traveled basically uninterrupted for around throughout our universe's history. So it saw the first stars. It saw the first galaxies. It traveled as the galaxies were forming. Again, mostly uninterrupted, just to show how sort of vast space is. It traveled through, it saw the creation of the first clusters of galaxies. And in the meantime, our solar system was being formed, our Earth was being formed, and we finally were able to create these detectors to measure this photon that's been traveling for so long, to give an imprint of the very beginning of the universe. And so you can see it reaches our detector and it finishes its incredibly long journey to give us some information about the very beginning of our universe. So I think that's really incredible that it's just traveled for so long and we're able to detect that. I talked about the sort of hot, dense time in our universe's early history. Something similar happens in the cores of stars. In the core, you also have these charged particles, and it's really hard for this photon to escape. It actually takes on the order of something like 10,000 years for the photon that's created in the core to even just get out of the star, right? And then to free stream to us for millions of years, right? So it's really like quite incredible that we're able to even measure this, right? So we're in the business of sort of collecting photons, right? Our detectors collect photons, and you can think of them as our detectors, the pixels on our detectors being buckets. And you can think of the photons or the light particles as being raindrops. And our detectors work by constantly staring at an object for a really long time and to collect enough photons or raindrops to get an image. Kind of an aside that I wanted to say is that, for example, our star generates 10 to the 42 photons per second. That's per second, right? And if we look at a galaxy, so before I go, 10 to the 42 looks like this. So it's a 1 followed by 42 zeros. So it creates this many photons per second. And there are around 100 billion stars in a galaxy. So if you are looking at a galaxy, you can add 11 more zeros to this. And so there's so much energy in the universe. And the fact that we're only really able to capture a few hundreds, thousands, maybe millions of these counts that we call them, really is sort of a testament to how just big, right, our universe is. Because when a star like the sun emits photons, it goes in all directions, right? And it's traveling for so long. And we're with our, with our space telescopes and ground-based telescopes, we have these detectors and we're capturing some of these photons to create a picture. I wanted to show you sort of how galaxies come into view in the first place. So let's see if I can reshare this. Okay, so here is just an example of this visualization that's created by the folks at Space Telescope Science Institute of the Hubble Ultra Deep Field. So like I said, we are staring at an object for a really long time. And you can see this slider on the bottom that kind of goes through how long we're staring at that object for, right? So if we point our telescopes at an object like a galaxy for 1/15 of a second, we're not going to see very much. There aren't any visible stars and there aren't any visible galaxies. As we continue observing, some of these fuzzy blobs come into view. So at 20 minutes, you start to see these objects kind of popping out, right? But you also see a lot of artifacts. There's a lot of noise. And it's hard to sometimes tell whether or not that noise is a real object or just an artifact or coming from somewhere else in the galaxy. But you can kind of suppress that noise if you continue observing. So here's at 81 minutes, you can see a distant spiral galaxy. You can see that the noise is much smaller. And most of these fuzzy blobs are actually galaxies, like with the exception of this random star that's in the Milky Way. And if you observe long enough, so in this case, nearly 100 hours of collecting light, you can start seeing the really faintest, smallest stuff, especially when you observe from space. You can see the faint galaxies, clusters of galaxies, irregular galaxies that are really young in their formation or that have merged. And altogether, this paints us a picture of all of the galaxies that we see in this field. So something that we do as astronomers, there are a lot of sort of surveys and telescopes that are that a lot of people are working on. Astronomers need to try to find the balance between either looking for a shorter amount of time at the same part of space to get these really faint young things, galaxies, stars, etc. Or they can look at the whole sky and but observe them for less time. So you get statistics, or you get information about how, like, what our structure cosmic web looks like, but you get much less detail for every individual galaxy. Usually this actually happens from these sorts of observatories. Typically take data from Earth, but there's an upcoming telescope at Space Telescope called the Roman Space Telescope, which will have a very large field of view as well. So this is the balance that astronomers face, that they try to figure out what their science is and how we can best serve the astronomy community. Okay, so going back to the presentation. Okay, so that's sort of the introduction. The brief outline that I wanted to make this talk about is, first, how do we observe galaxies, which I kind of gave an introduction here. Then taking what we observed, how do we measure those galaxies? And then taking those measurements, how do we analyze galaxy properties? So observing galaxies, we are collecting these light photons to fill our buckets. So since Yerkes Observatory, I've upgraded to the Hubble Space Telescope. The Hubble Space Telescope is really like a marvel of scientific engineering. It really helped us discover a lot about our universe. And it's quite remarkable the depth to which it can see galaxies. At its most basic, it's basically like a floating school bus in space. It weighs around 27,000 pounds and is 13.3 meters long, so a school bus. It has a pointing accuracy, and this is important, of around 0.007 arc seconds. What does that mean? It's very impressive. It's if one of you viewers who are watching right now are in Pittsburgh, and which is around 200 miles away from Baltimore, and you hold up a dime, like a coin, and I shine a laser at it, it would directly point in the middle of that laser. So it's the ability to shine a laser beam on a dime 200 miles away. So hi, friends in Pittsburgh. It contains more than 100 terabytes of data. And it currently produces around 10 terabytes of data a year. So that's why we need so many amazing scientists to reduce all that data and to analyze it. And there's a lot of science that has been published with Hubble data. I mean, it really sort of revolutionized astronomy. I kind of gave you a brief overview of what makes Hubble so extraordinary, but I wanted to drive the point home. What makes Hubble so extraordinary? Apart from the pictures that you see, these beautiful images that look like this, which is my favorite cluster, by the way. This is a field of max 1149, and it's the best. I have it like on a blanket. Pictures like this, or videos like this. Or helping us generate these visualizations, like you see here. This is a visualization that actually Frank Summers worked on, which is really cool. It is a visualization for Hubble's 25th anniversary, where they did a fly-through of the star cluster Westerlin 2. And as we're going through this star cluster, as we're going on this flyby, you're seeing all of this gas. This is like a stellar nursery. This is where stars are being born. And as you go close to the center of this cluster, you see these really beautiful stars. So Hubble has done a lot, has created so many beautiful images. And it has helped us answer some of the most fundamental questions that we have in astronomy and astrophysics. From the smallest scales, so size of our solar system, to the cosmic origins of the universe, the very beginning of our universe. So here's an example. Hubble was the first to spot auroras on Jupiter, exploding stars, or supernovae in the Milky Way. distant galaxies merging, and the early universe. So it really like covered a large swath of time and helped us understand all of these different amazing things about our universe. With Hubble, we've also, as I've shown you, we've looked really deep and really far. And I want to just give you the scale that we're looking at. So let's see if it'll start. Okay. So I wanted to show you what the Hubble Deep Field looks like. And the way that this program was imagined was that the director has discretionary time that they can use to look at whatever they want, more or less, with Hubble. Has 10% director's discretionary time. And Robert Williams decided to look at nothing. So we picked a dark spot in the sky. I'm saying we as if I participated in this. I didn't. It was the work of very, very impressive scientists before. So we looked at this dark patch of sky where we expected that there would be nothing there. And we didn't point next to the moon. The moon is just there for size comparison, just to show you how small that patch really is. And it's around 1/13 of the total area of the sky. And we fully expected not seeing anything there. And when we looked, out came all of these beautiful galaxies, thousands of galaxies in what is now known to be as the Hubble Deep Field. So we just pointed our telescopes in that direction and looked for a really long time and were able to see this. So each of these specks is a galaxy containing, I'm averaging like 100 billion stars. Each one of these little smudges on the screen. And so this totally revolutionized, right, our understanding of how big our universe is, how many galaxies there are in the universe, how far we can see. And so here's just another visualization of one of the successors to the Hubble Deep Field, called the Hubble Ultra Deep Field. I'm going to play this just to, again, show you the scale. So we start with seeing the constellations and the whole kind of part of a big chunk of the night sky. And we're zooming in, and we're zooming in, and we are continuing to zoom in very, very far. And we see the Hubble Ultra Deep Field. And so these are some of the youngest galaxies that we can observe that really give us some understanding of the beginnings of our universe. Okay. So scientists, after doing all of this and kind of this being really impactful work, you know, scientists at Space Telescope and elsewhere thought, well, okay, how can we push even farther than that, right? So you can see that you have the Hubble Deep Field kind of pushing at like 1.5, when the universe was 1.5 billion years old. So we see galaxies when the universe was 1.5 billion years old. The Hubble Ultra Deep Field pushed to the age of the universe of around 0.9 billion years old. So we are looking even farther and we're seeing even smaller, even younger galaxies. So what can we do to probe even farther, other than just staring for longer? So some people came up with a project called the Hubble Frontier Fields. So the Hubble Frontier Fields is a survey of 6 really massive clusters, leveraging something called gravitational lensing, or nature's magnifying glass, that allows us to push even beyond the limits of Hubble. How? So before I get into how, I just wanted to show you what they look like. So these are the 6 clusters that I basically did my PhD thesis on. And then on the bottom, you see 6 sort of what we call ancillary fields, which is just a field that's separated by some distance from the center of the cluster. So how do we use this data to leverage nature's magnifying glass? So what is so it's called gravitational lensing. What is that? You can see kind of in the schematic here, you have the observer telescope on the left, you have a foreground galaxy in the middle and a background galaxy in the back. And basically what happens is that the foreground galaxy or galaxy clusters warp space in such a way that it bends the light that's coming out from this guy over here, so that we get more of the light from this background galaxy, and we're able to push really, really faint. A nice schematic of how this works. So imagine, you can actually do this at home. If you take a candle and you take the base of a wine glass and you put it in front of the candle, depending on the tilt that you put the base of the wine glass, you can see it creates these sort of arcs. And depending on the angle, it changes the way that that light is distributed once you're looking at it from the base of the candle's perspective. So if you can see that if you're looking at it straight on, you're creating this, basically what comes out is this ring around the base of the wine glass. And you can see that it looks brighter, right, than the original candle. So the same kind of principle applies for gravitational lensing. I can give you another example. If you imagine a trampoline, right, and you roll a ball on the trampoline at a 45-degree angle, it'll probably, if you throw it or if you roll it straight enough, it'll probably just fall off of the trampoline, right? Now, let's say you take a really heavy bowling ball, if you have one at home, and you put it in the center of that trampoline, and you throw the same ball, or you roll the same ball, it'll probably do like a curve. And if there's someone on the other side of the trampoline, they'll be able to get it, right? So in the same way that all of the light that was coming out in like kind of radially outward, gravitational lensing warps space in such a way that it's able to focus that light to the observer. And what we see looks like this, kind of similar to this wine glass. So it's just some facts. The typical magnification is around 10 times. So you can see galaxies 10 times brighter than they would be if they weren't distorted by this gravitational lensing. It preserves surface brightness, and the lensing is achromatic. So what does that mean? It means that it doesn't change the color of the galaxy or the source that we're observing. You'll see why this is important in a little bit, but just as a teaser, color gives us a lot of information about the physical properties of a galaxy. And gravitational lensing is purely a geometric effect. So it doesn't change the sort of the color of the galaxy. And so it's really useful in that way. Here's another kind of more practical example of gravitational lensing out in the wild. You can see the galaxy cluster right in the middle, and you can see this sort of blue arc-shaped galaxy. And all of these things that are circled are from the light from the same galaxy. And you can see that it's being stretched out, it's being magnified in brightness, and you're able to measure. So the nice thing about this stretching out feature of gravitational lensing is that you can really measure things on small spatial scales of what happens in that galaxy, right? Because it's so stretched out, you can kind of see what's happening at every part of that galaxy. Whereas if it were just a point source or a little smudge, you wouldn't really know what's happening in the center versus the edge of it. There are people who work on reconstructing these galaxies. So here's an example of that. There's this team that worked on reconstructing what the galaxy might have looked like had it not been warped by the central cluster. And also figured out where it might be if it weren't warped by the cluster. So in this case, it looks like that the original position, if there wasn't any warping happening, the cluster would have been somewhere here, right? In the same way that when you look here, the galaxy is actually directly behind this foreground galaxy, but it looks to us when we observe it kind of in this ring around the galaxy. Okay, so we have this amazing data set, this really deep data set where we can push Hubble really far. And I guess the basic question that we're asking is, how do we go from these really beautiful images of the jewels, galaxy jewels in the sky, So something that looks like the picture on the left to something that looks like the picture on the right, which is admittedly less beautiful, but still very important for our understanding of galaxy properties. So this is what I did my PhD on. I was generating galaxy catalogs or source catalogs for the Hubble frontier fields. I'll show you an example of that. These are the images that I worked on a regular basis. So I don't work on like color images. Really think back to how I said that our detectors basically collect photons in a bucket, right? So what you have is a sort of, in every pixel, the camera tells you, is there a photon, is there a raindrop photon here, or is there not? And so this is really kind of like a grayscale, like black and white image. And this is observed in a single filter, which I'll talk about in a bit. So, okay, so I run this algorithm called source extractor, which extracts sources, so very self-explanatory. And basically what it does is it scans kind of line by line to see where is there something bright and where is there nothing, right? And we can get a list of sources from after running this algorithm. So this is what that looks like. Every single blue dot here is a detected source. I wish I could see you guys in front of me to ask you how many galaxies you think is in this image, but I'll just tell you. There's around 3,500 galaxies just in this small piece of sky. And it might not look like it, so why don't we zoom in? So let's zoom in to this area. So here, again, to remind you, every single blue circle is a source. Every single smudge is mostly, on average, a galaxy. And I just wanted to point out these sort of, remember how I was saying that gravitational lensing distorts background galaxies? You can see that kind of happening here, these arcs. So that's not what the background galaxies look like. They're actually pretty distorted and stretched out. And it's not usually a perfect circle, right? Or it's not usually that those galaxies are kind of like perfectly circular around the center. It depends on what is distorting your space in the foreground, right? So if you have a bunch of different galaxies doing that, it won't be spherically symmetric, but you'll see these arcs appear in your images. Okay, so we can zoom in even more just to drive that point home. Here's again an example. Every single little smudge is a galaxy, and every blue circle is where we've detected that galaxy. I think that this is pretty good. I think I did a pretty good job. But you might say, for all those eagle-eyed people in the audience, you might say, well, I'm seeing some sources missing. You know, maybe there's one here next to this really bright object. Maybe there's one here next to this really bright object. And so this is on very small scales, but on large scales, this happens because we have these really massive galaxies that are really bright. And so there's the problem, even with all of this amazingness of gravitational lensing, there's this problem that these galaxies are really bright and can obscure the light from the really faint stuff behind it. So detecting galaxies in cluster fields is difficult. It's difficult because you can see the sort of mess that's happening in this cluster. There's the really bright stuff, and there's also this kind of amorphous gas that is it's just basically hot gas and stars that are free floating between the cluster galaxies. And so, well, one thing that we can do is try to model it and remove it, right? So here's another example of one of the galaxy clusters. This is another example of one of the galaxy clusters. Here, the coloring, even though it's sort of purple and yellow, it's just false coloring. This is the same sort of grayscale type image that we saw earlier of a different cluster because I want to see them all shine. And where the purple stuff, or the purple pixels, are where there's very little light or less light, and the yellow parts are where there's a lot of light, right? And so we know some stuff about galaxies, we can kind of model them with a, we can kind of approximately model them with an analytic profile. And so that's what I did. I tried to model the really bright stuff. So that's what that looks like, the bright stuff and the faint kind of diffused light that is around it. And we can subtract out that model and we get something that looks like this. So you can see that all of this excess light has been removed, and now has been removed because for me, it was kind of preventing me from doing my job, but probably for the cluster people, they're very essential to do their science, right? Because they need those cluster galaxies. And you can see kind of all of the small faint stuff in the background. So here's just that whole process from left to right, where you have the original image, model, and the subtracted out model where you can get to the really faint stuff. Okay, up until now, I've been sort of telling you about looking at a single image. And the single image is being looked at in one filter. So this is an example of just a single image being looked through one filter. For the Hubble Frontier Field, so this looks kind of complicated, but don't worry. The only thing you need to know is that each one of these graphs, or each one of these like colored sections, correspond to a different filter that goes from really, that goes from the mid or the near ultraviolet to the near infrared. So we're going from, and you can see kind of this like rainbow of color on the bottom. So it's going from kind of purple all the way to red. And we looked at the same object in each one of these different filters. So remember I told you that color is important. It tells us different things about the processes that are happening in the galaxy. And so we observe these frontier field clusters in, count them, 3, 6, 9 wave bands to tell us about the physics that is happening at each one of these wavelengths. So I just wanted to show you this for a second, and I'm going to go into it more right now. The multi-wavelength universe, more than meets the eye. So we're going to talk about color and wavelength and how that tells us information about galaxies. Okay, so if you've ever been to a place where the sky is dark enough that you can see the Milky Way, which I have not until 3 years ago, again, for the same reason as I mentioned earlier, that in New York you don't see dark skies. But if you were able to do that, you would see something that looks like this, right? This is sort of looking towards the center of our Milky Way, and you can see that it looks very dusty, right, with a lot of starlight around it. That's what it looks like. It's really cool. It's really like quite impressive when I saw it for the first time. It was at Joshua Tree. Also, for folks in California, Joshua Tree is so pretty to see the Milky Way from. Okay, so if we take that Milky Way and we kind of like rotate it, this is known as the galactic plane, right? So now you see our galaxy edge on the Milky Way, where you have in the center, you have the center of our galaxy, which also happens to host a supermassive black hole, and the spiral arms are out here. And so I think that you are somewhere there, which is around 7.5 kiloparsecs away from the center of our Milky Way, which corresponds to around 1.4 times 10 to the 17 miles. So 1.5 and 16 zeros after that miles away. So wave hi to yourself. So this is just something that we would see, right? You know, if you went to something like Joshua Tree, you would see something that looks like this. So we're seeing it in the optical waveband, which is what our eyes are sensitive to. But you may have heard that there is a lot of different types of electromagnetic radiation, right? So there's the visible light, which is what we can see. And then there's things like the ultraviolet, which is why you need to wear sunglasses, X-rays when you go to the dentist. There's also infrared, which you can't see, but you can feel because it comes off as heat. I don't know if you've ever been to to any of those science museums where they have like an infrared camera and you stand in front of it and like your core is like really bright, but your hands and feet are like bluer because they're less hot. And so even though we can't see any of these wavelengths other than the visible one, they all tell us information about what's going on. They all hold some secrets about the physics that's happening in our universe. And so if you take that same Milky Way that I just showed you, you can observe it in a bunch of different wavelengths. And when I say wavelength, I want you just to think about an energy, right? So when things are really blue, so at the very bottom here, gamma ray, short wavelengths correspond to really energetic stuff. And long wavelengths correspond to much less energetic stuff. And then there's everything in between, right? So in the optical, which is right here, you see this band of our like galactic plane. But then if you look outward, right, you can see in the gamma ray the most energetic parts of the Milky Way. So that tells you about the energetic, like very energetic and hot physics that's happening. In the infrared, you can say something about star formation. So you can see like different clumps come out and dust. And you can see that that our Milky Way looks very different depending on which wavelength you look at it from, right? I mean, these are all false colored, but sort of the features that come out look different. And this is kind of related to what Frank was talking about in his introduction. I promise we didn't coordinate that, but that was really like nice, like good timing. Because at different wavelengths, it tells you about different energetic processes that are happening within whatever you're looking at. Here's just another example of that. So this is called the whirlpool galaxy. So in the optical, you have optical light that comes from stars, which are around the size of the sun. So we can get physics on that. In the X-rays, which is really energetic, you get information about the hottest regions of gas where atoms are ionized. And remember that ionized just means that atoms are charged, or that you have charged particles. And then on the opposite end of that, you have cold gas in the radio. So radio waves reveal regions of gas cool enough for something like CO2 molecules to exist. So all of these things tell you something different about whatever you're looking at. That's also why you have, I don't know if you've heard of all of these different telescopes, but if you have, you might be wondering, why do we need so many? Well, we need so many because we want to cover the whole like sort of gamut, right, of wavelengths and of energies to tell us things about whatever we're looking at, about our universe. So you can see Hubble is right in the center, around the near UV to the near IR. And the other two telescopes, so we have James Webb that you all have heard a lot about, and also Roman that will be launched soon, that will do really cool science on really large scales, looking in these sort of wavelengths, and similar wavelengths. And then you have others that fill in the gaps for different science that people want to do. But here's another link. I'm going to skip this, but I encourage you to look at it. So the SDSCI's view space is really cool. It has a lot of cool visualizations, a lot of cool, like there's bars at the bottom where you can look at, merging galaxies. You can look at how colors affect what your picture looks like Frank was showing with Crab Nebula and others. And so I really encourage you to take a look at this. I just don't want to stop sharing my screen and resharing it and etc. Okay, so what does that actually look like, right? When we are trying to measure the brightness of something in different wavelengths, what does that look like meaningfully, right? What do we actually sit down at our desks, use our computers to analyze? So here's an example, and this is really just forget about, don't be scared. This is going from the from the X-ray all the way to the radio wave, part of the spectrum. So let's strip this down into only things that we care about, right? To simplify this. So on the y-axis, you have the brightness, and on the x-axis, you have the wavelength. And remember that wavelength is just a proxy for energy. So on the left, we're going from the X-ray to the UV, to the optical, to the IR, to the submillimeter, to the radio. So from the shortest to the longest wavelengths. And we measure a brightness of this one galaxy at all of these different wavelengths. So in the X-ray, for example, you can see that there's some kind of trend there. And those points, that brightness, is telling us about the supermassive black hole at the center of that galaxy, which is emitting a ton of energy. And so that tells us something about the black hole. If you're moving redder, right? So you're moving towards the optical, that starts to tell us about stars, something called the stellar continuum in that galaxy. And if you move farther to the IR, where you see these like green points, that is actually, again, similar to what Frank was saying earlier, that is connected to the supermassive black hole that is emitting these really energetic photons. It's getting reabsorbed by the gas that's around the dust and the gas that's in the galaxy. And then that is being re-emitted, and that re-emission is in the red in the IR. And so just from these data points, you can say something about all of the different physical processes that are happening there. And then I am totally not a radio expert, but I think the radio has something to do with the supermassive black hole as well. I think you guys heard about that in some of the previous public lecture series talks. Okay, so I hope that, that I convinced you that you are able to look at these complicated plots, right, and get some information from them. So how do we actually know about that physics? How do we know that, black holes should emit at this wavelength and stars should emit at this wavelength? We have models, right? Because we know something about the fundamental physics that's happening and what that physics should look like, right? So if we know that, okay, we have really energetic photons, then probably we're going to observe it in the X-ray, something like that. And so we create models. So going back to this plot that is hopefully less scary now, in each of these, you can see there's the blue curve, the red curve, the green one, the purple one, the orange one, etc. All of these are models that we're able to fit our data to say something about our galaxy, right? And so because we're able to kind of tweak the parameters of the models based on the physics that we know, we're able to say, okay, this galaxy has a supermassive black hole. It also has this many stars. It's, this massive. It's this old, et cetera, et cetera. So I work mainly in the optical. So I work with HST wavebands, so from the UV to the IR. And here is just, again, this might look scary, but I promise we can do this. So let's do it together. So each one of these colored curves is a filter, right? So in this case, if we looked at an image, we would observe it in 4 filters. And in each filter, we can get a different measurement for the brightness of a galaxy, right? So we have 4 points. And this black thing that's kind of moving is the spectra. It's sort of our model of what a galaxy should look like, or how much energy a galaxy should emit as a function of wavelength. And we can use that model to fit our 4 data points to say something about, in this case, how far away the galaxy is. Okay, so one more kind of complicated plot, but again, stick with me. So forget about everything here in this plot. Just focus on the fact that the y-axis is the brightness in the top 2 panels, and the x-axis is the wavelength. And again, we're going from bluer, from the UV, to, well, this is actually to the optical. And I just wanted to show you this because it shows 4 different images. So kind of putting together the images and what we measure, it shows 4 different images of looking at the same part of the sky, right? And so you can see how they look different in these different filters because we're probing different physics of of whatever system they're looking at in this case. And so we get a data point per filter, so we can measure the brightness with that source extractor software code that I talked to you about earlier. And we can measure the brightness in each filter band and put it on a plot of our model of galaxies and say something again about the galaxy, how far away it is, how old is it, what's the stellar mass, et cetera, et cetera. And so this is what I do with the frontier fields. I'm going to wrap this up, so no more complicated plots. Sorry about that. Just to show you kind of how exciting it is to be an astronomer right now, and how exciting it is, hopefully, for you all to follow astronomy news. Because Space Telescope just recently launched JWST. We talk about it a lot. It's really cool. But you can see here that it's probing there's some overlap with HST. And so this is why HST is still very important. But it overlaps a little bit with HST, and it's probing kind of a different part of the electromagnetic spectra to tell us things about the oldest galaxies. Here's just kind of a summary of that, kind of a summary of the history of the different surveys that scientists, really talented people have done over decades. So in the 90s, you had ground-based observatories, and you still do, and they're looking at really large swaths of the sky instead of going really deep. But they were able to see up to galaxies that were at 6 billion years after the Big Bang. The Hubble Deep Field you saw, it probed galaxies 1.5 billion years after the Big Bang. The Hubble Ultra Deep Field probed even younger galaxies at 800 million years after the Big Bang. And this is an old graphic because it says future, but JWST is already doing this, and it's seeing stuff between 200 and 500, maybe not 200 million years after the Big Bang yet, but around 500 million years after the Big Bang. And it's seeing the universe's first stars and first galaxies. And so I'll leave you with this. I think that, again, this is a very sort of exciting time to be part of this field and to follow the field in the news and at Space Telescope and at your local observatories or other places. I think I'll end with this, that one of my favorite parts about being an astronomer is that you're really sort of able to say something about the evolution of the universe through cosmic time, right? So we really are we're time travelers that are able to say something about what the beginning of our universe looked like up until now. And sort of we really are the universe observing itself. And that's pretty incredible. Thanks for listening. That's it.
Okay. Thank you, Amanda. That was wonderful. Really, deep in places, but, in order to really understand how we derive these galaxy parameters, it wouldn't be deserving of PhD if it wasn't deep, right? So I had a question that I thought some of our people in our audience would have. All right. So in doing this, you're getting the brightness in like these 9 different filters that you showed. Okay. Mm-hmm. From that, you're able to get a photometric redshift, which is a measure of the distance. What do you also do about the galaxy shapes? People were chatting here about spirals versus ellipticals, and they're actually wondering why most things are spirals, but that's not quite your expertise. So do you get good characteristics on the shapes of these galaxies as well?
Yeah, so thanks for that, Frank. So I showed you that we were able to model some of those galaxies when I was trying to model them and remove the contaminating cluster light from my images. So we are able to model it. Their shapes look different as a function of wavelength. So they do. So you will see, star-forming regions in one filter and maybe like the bulge of the galaxy in another filter, and you put that together to say something about the galaxy. But it's true right now what we were doing was just drawing kind of circles or apertures around each galaxy to say something about the total flux. But you can model them, and we've been modeling them analytically because we kind of know what a galaxy should look like. And so we're able to approximate it as an analytic function and do that modeling. And those modeling parameters that we actually extract change, right, as a function of wavelength. So you need to fit different models for each image and each different filter. I don't know if that.
Right.
Yeah.
I mean, I'm trying to get it explained for the public and on that level, because you're able to, from the shape of the spectrum of an elliptical galaxy versus the shape of the spectrum of a spiral galaxy. But just to reiterate in terms of the redshift and the redshifting as it goes across, just make sure people understand how that spectrum, as you showed in that animation, just sort of moves to longer and longer wavelength. And of course, great reason why we need the Webb Space Telescope, right? Okay, Grant, you've been following the YouTube chat a little more tightly than me. Why don't you come and join us and see if you've got some good questions from our audience out there?
Absolutely. You did a very thorough job explaining, so people are having less questions than normal, which is a very good thing. You're doing a good job. So we'll start off kind of piggybacking off of what Frank said. How is it that you differentiate a target that has redshifted versus one that is simply closer at a different original color or temp? If they appear to be similar, how do you tell the distance apart?
Yeah, so that's a great question, right? I was driving home the point that color matters, but if you have something in the foreground that is red and something in the background that is really far away that looks red, you might have some issues, right? The way we do that is, I talked about these spectra, right? These models that we fit to our galaxy fluxes. The galaxy that is really far away will typically have a different spectra than a galaxy that's very close by in red. And so you can if you fit your models to your fluxes or to your galaxy brightnesses, you'll see that they actually look different. One will be the redshifted one, the one that's far away will be redshifted towards the redder side, because as space expands, I didn't talk much about redshifts, and maybe I should have, but as space expands, it stretches out a photon, right, causing it to look redder. And so fundamentally, the light that's emitted from that galaxy is still, intrinsically one thing, and we just see it as redder because of this redshift thing. And so all you have is the spectra just being moved over to the redder part of to the redder filters. Okay, and so that's how you tell the difference. Yeah.
Yeah. So it's that's really important that you have, I don't know how many base models in terms of what a spiral looks like, an elliptical looks like, or other things. You have, like, I don't know, a set of half a dozen of those, something like that. But each one of those then has to be redshifted to try and fit. So you've got this your base models plus all of the redshifted versions of every one of those base models to try and fit to your data, right?
Yep, exactly.
Okay. So based on that, the more you observe, the more complex and accurate the models can become. Okay. And this ties back into what you meant about gravitational lensing being achromatic, that it doesn't change the character of the light, right?
Yep, that's right. It retains its color and brightness in each filter.
But of course, it does change the shape of it, right? And so, trying to figure out whether it's a spiral or an elliptical or an irregular for lens galaxies is obviously quite difficult.
Yeah, exactly. It changes the brightness, but it doesn't, because it magnifies it, but it doesn't change the relative brightnesses between each like wavelength.
All right. So therefore, all of these relative brightnesses that you showed in that wonderful animation still hold true.
Yep, exactly.
Cool.
Thank you.
All right.
Okay. In doing gravitational lensing and mapping, how were the image selections made to find possible image arcs, or were they already known areas with gravitational lensing present?
So these were known areas. So how did we decide which clusters to point at? Like, or how
No, I think he's asking when you're when you're dealing with gravitational lensing, do you select places or images that you know gravitational lensing has taken place, or is it something that you do kind of on the fly as you notice it in your data that is returned?
Sure. Yeah, so that's a great question. In the case of the Hubble Frontier Fields, we pointed, and again, by we, I mean the scientists at Space Telescope and not me, pointed to known massive clusters.
Okay.
There are efforts by, collaborations, by other collaborations, like the Rubin Observatory, if you've heard of that, or the Dark Energy Survey or whatever, to find lenses and to find kind of where lensing might be occurring, to say something about, again, the cosmic web and the structure of the universe. But for the case of the frontier fields, we pointed directly at 6 known massive clusters that didn't have a whole lot of stars to contaminate the field.
Okay, and I think the question might also be saying, when you see an image that's stretched out, I mean, you can have stretched out elliptical galaxies, really long elliptical galaxies. How do you know whether it's lensed or not on that?
That's another great question. This person should totally be a scientist and astronomer.
We have an audience that comes faithfully and asks good questions.
Yeah, that's awesome. Yeah, that's a great question. So some they're obvious, right? Like the color it's blue. You can kind of pick out like features that were of a spiral galaxy, but you can see that it's just like stretched out. It's usually pretty apparent in these really massive cluster fields. There's something else called weak lensing, which is just galaxies being lensed slightly by all of the matter between that galaxy and us, the observer. There, it becomes much harder to tell whether or not the galaxy is actually being lensed, or that's just what it looks like. And so that is really a game of statistics and simulation. So there are people who look at this on like very large scales, and they see, okay, well, probably there's a lot of matter here, and that's why it is lensed ever so slightly, and there's this much matter in this part of the sky. But for the purposes here, they're mostly distorted enough that you can tell that they were lensed.
Cool. I know we've had a couple people come on and talk about gravitational lensing with Hubble. I'm interested to know, what is it that you look for in the data from Webb that tells you that it might be gravitational lensing? Because it's not necessarily everyone's mind. They think astronomy, they think pictures, they think Hubble, even though Hubble had other instruments. It's just the common conception there. What is it that you pick out of the data that tells you, oh, this is being lensed?
Yeah, so I mean, firstly, a lot of these, like the frontier fields, for example, are also being observed with Webb. So we already know that the galaxies there, we kind of know that, like, okay, these are lensed galaxies. We have a lot of information about, or we extract and measure a lot of information about how massive things are, right? So if we know that there's a really massive galaxy, we can probably assume that the things behind it are going to be lensed in some way. And so that's sort of, I personally don't, my work just involves detecting and measuring those objects. I don't search for lenses, but you should have kind of similar distortions of galaxies that will show that they're lensed.
And also, doesn't it, the appearance of multiple objects with the same redshift and similar color ratios indicates the lensing, right?
Yeah, good point.
Right. So somebody commented that when you were doing the subtraction of the intracluster light, that it's sort of like finding a planet around a star, looking for exoplanets and subtracting off the point spread function of a star. It's not anywhere near the contrast ratio, but can you comment on that a little bit?
Yeah, I don't know anything about exoplanets other than what you just said. Yeah, I mean, the comment is that it's a really hard job and it's important to get right. And yeah, like a lot goes into it, but you're totally right. That connection is great. It's kind of a similar process, a concept, right? You're trying to remove something really bright to get to something really faint. And how can you remove something really bright? You can try modeling it and taking that out, because otherwise it's, it just contaminates what you're actually trying to get at.
And I guess
Webb is, sorry, go ahead, Frank.
I guess when this comment was made, I was thinking to myself, well, what's the contrast ratio between the bright galaxy and the faint galaxies that you can pull out? Because, I mean, galaxy modeling can't be quite as clean as PSF modeling. I mean, we get huge amounts of data for point spread function modeling. So what's the sort of contrast ratio? Is it 1,000 to 1, 10,000 to 1 or something that you can get?
Yeah, that's a good question. So one thing that I will say first is that, again, it's hard to do. One way we can kind of make sure that we're doing it right is by simulating galaxies and like putting that in the image, and then seeing, like, after we do this modeling, do we recover what we know that simulated galaxy's brightness should be. So we have to do a lot of these checks. The galaxies in the cluster are at around between magnitude like 16 and 19. So pretty bright, and we push really deep. So part of that is thanks to Hubble's resolution, right? Like, we can resolve really small things. So we're able to find it, but we just need to make sure that it's not biased from that like looming brightness from the really bright galaxies, right? So we're typically able to find it. We can find more when we take it out, but when we take out the cluster galaxies, but we're able to find small stuff. The ratio, so again, between 16 and 19 is the brightness of the clusters. And I would say like the galaxies that we can detect behind it are like magnitude 24, 25. Yeah.
Cool. So a factor of several hundred at least.
Yeah.
All right. Okay, Grant.
Magnitudes, and nobody knows what that actually.
Don't worry. I'm comfortable translating. That's my job.
I appreciate you, Frank. I know the audience does too. Okay, would you expect to see fewer lensing objects the further back in time you look, as there might be fewer massive galaxy clusters?
That's a great question. Let's see. So if you observe, so right now we're not really able to observe galaxy clusters very far away. Galaxy clusters that we're looking at are actually pretty close to us, at a redshift of like 0.3 to 0.5. So it's fairly close. I guess if you were able to resolve a galaxy cluster that's very, very far away, I don't know if you would be able to even see much of the lensing, but if there's less massive stuff, so you would still see the sort of micro lensing, right? Like, you would still see lensing no matter what. If there's matter there, you will see lensing, and that's what I was saying earlier about weak lensing. Yeah, you probably wouldn't see it as pronounced, and you might see less of it.
And I think that question also hits upon the fact that it takes time for a massive galaxy cluster to form. So, I mean, we don't expect massive galaxy clusters at redshift 7 or 8, right? Yeah. But, that's one thing that Webb will be able to actually see more clearly than Hubble did, is when do we first start getting these massive galaxy clusters? And, well, of course, how do you define what a massive galaxy cluster is?
Massive for its time. Yeah.
Yes. But I mean, they should get larger over time, because gravity just assembles more.
Right.
And then there's also the fact that, like, if I'm correct, sort of the prime lensing distance is like twice the distance to the cluster,
Yep.
right?
Hmm.
So if the further away it is from us, then the further away the stuff that's going to get lensed has to be, right?
That's right. Yep.
Okay. Cool.
Okay. All right. So let me grab another question here.
All right. Let me go through my notes, see if there were any other questions that I noted down.
Oh, I like this. This isn't quite your field, but I'm throwing this to both of you anyway. What would you define the difference between a telescope and a collector? And why would you need two separate instruments aside from capturing different types of wavelengths?
I guess in the story that I tried to paint, a telescope is a subset of the broad collector, collects photons. Your eyes, I guess you can also call collectors. Yeah, so a telescope is a subset. Why would you need different cameras or instruments? Precisely for what you mentioned, because every detector is sensitive to some specific wavelength. And we need those wavelengths to say things about our universe.
That's one of the reasons I think that Hubble and JWST are working so well together is they overlap a little, but they're able to look at different wavelengths and give us significantly different information, even though they are both collector type arrays, I suppose, stations.
And, that's
right.
one of the things you referred to with the view space sliders, where the Eagle Nebula, where you can slide from visible to infrared and such, or take Cassiopeia A, you could do a slider for that, it's going from all the way from radio to X-ray. Having multiple telescopes in multiple wavelengths, as you made this point very well with the galaxy, shows you different physical characteristics. So I had a question that I thought people might have. When you did the original thing with the view space and doing the long exposure of the deep field, when you started out there was that chip gap seam and everything, okay? But you didn't really explain how all these exposures gets rid of some of these things. So can you talk about the co-adding of images and the dithering and such, just so people understand how that you don't just open the telescope exposure for 97 hours, right?
That'd be too easy, right? Yeah. So what people have, again, like really talented people have come up with different ways to reduce the noise in your image and to get your galaxies to shine brightly. One way that we get rid of the artifacts is by if we take an exposure and we're looking at our galaxy, we know that there's a chip gap or some kind of artifact right in the center. If we do something called dithering, if we move it a little bit up or a little to the side or rotate our camera a little bit, we'll get another exposure of that same galaxy, but shifted. And so now that artifact is in a different part of your original image. And if you do this enough times, you can stack those images together that were taken kind of slightly offset from each other, and you can get rid of those artifacts because they fall on different parts of the galaxy, and they'll fall out once you stack those images together.
So this is a place where dithering is a good thing.
Yep.
My wife and I discussed dithering as a bad thing when we're trying to choose a movie for streaming, and she's dithering about which one she wants to watch. But dithering in astronomy is a different thing, and it's much, much, much better.
Yeah.
Grant, you have one more question?
Yes. Do we
right,
want it to be
one.
a serious question or a personal question?
It's up to you. You are in control on this.
I like this one. We're doing it. Hypothetically, if you were gifted a whole week of personal use with any telescope, what would you use, and what would be your specific observation target?
Wow.
You could
I was,
hijack the tack. That's all
if
you
I
got
can
to do.
have director's discretionary time and just look at it, look at anything. Um, that's a great
Pagul
question.
time.
Yeah, what?
Pagul time.
Yeah, I don't know if that's really like interesting enough. I prepared for a lot of things, but not for that question. Um, I guess I would look at. Is it boring to say I would look at say kind of like what the Hubble Deep Field people did, just looked at the same point of the sky the whole time, to see faint how faint of galaxies we can get. The cool thing about this is that we have a good understanding of galaxies that are close to us. But the way galaxies look and the way galaxies form really far away from us, so at the beginning of the universe, look very different or substantially different, let's say. A lot of them do. So right now we think about ellipticals and spirals, right? Very young galaxies typically look like blobs. They're like irregular. And right now there's like ongoing science about these really faint galaxies, these really young galaxies, and trying to understand, will they break lambda cold dark matter or will they not? Does it match what we expect the beginning of our universe to do? And so I think that would be my answer. And maybe, yeah, I think that would be my answer, just to look even farther, stare at a part of space for a really long time and see what comes out of it.
Well, I don't know if you will get that time, but eventually the web is going to do that in some way, at least in aggregate over the years, we will get some great stuff. And I too look forward to that. The question is, how quickly can galaxies form? How quickly can these clusters form? And it's really fun that in the next decade, we're going to get those kind of answers. So I look forward to that as well.
And
You
if
can
also,
add another. Oh, go ahead.
sorry.
You're fine.
There is just another, if we can figure out a way to look at really before like the CMB, right? So before 300,000 years, when the universe was 300,000 years old, that would be really cool. And things that are able to, I mean, this is not imaging anymore. This is like purely like hypothetical. But things that are able to escape from before the CMB are like neutrinos, for example. They don't get trapped in the like ionized plasma that photons do. And so if we can like observe like neutrinos for a really long time, maybe we can say something about the even earlier universe. But that's another like sci-fi.
Yes, right now neutrino astrophysics is neutrino observational astronomy is science fiction for now.
Yeah.
All right, thank you, Amanda. This is wonderful. We have run out of time. Well, thank you. And everybody, next month is not until June 22nd. We will have 2 talks on the Nancy Grace Roman Space Telescope. One talk about Nancy Grace Roman, and the second talk about the mission and the science that will be done with that telescope. Please join us then. Until then, thank you for watching.